Okay, it's always nice to see progress, and of course, Paul and Neil and Clint have put a lot of effort in getting us this far. So it's really great to see this is finally taking off the ground. And Paul, I was impressed looking at those applications of Kinesim 5. So that's really nice impact of nuclear war and things like that. So of course we don't get to do everything as a at CCCMA. So all these unique applications, they are nice to see. Okay, so I'm going to talk about the land component in Kinesim 5, plus new developments for CMIP 7. As Jason said, all of us are really busy trying to put together our next version of the model for CMIP 7. So I put together this talk over the weekend, so it's not as organized, but I think I got everything here. And of course, we have a big land group now at Climate Research Division, and it includes all these people listed here. A lot of them are new hires. Okay, so here's the structure of our land surface scheme. A picture is worth 1,000 words. And you can see, and this is how the model looks like for Kinesim 5. And you can see that the model simulates the physics of the model, which was written by Diana Versaghi in 1990s. And at the time, the model was called Canadian Land Surface Scheme Class. And it does the energy, water, and momentum fluxes, all the physics at the land surface. And then in 2000s, I was hired, and then we were able to put in carbon cycle in the model. And as it's implemented in Kinesim 5, the model simulates all the carbon fluxes, the land atmosphere CO2 fluxes, and the processes are shown here in magenta. But it also simulates dynamic wetlands. So wetlands expand and contract depending on soil moisture simulated by the physics. And there is wetland emissions from wetlands, and there's also methane uptake simulated by the soil. Now, in this figure, I show here that the model is capable of N soil layers, and then you can have bedrock beneath it. And the difference here, of course, is soil is permeable and bedrock is not. The water cannot percolate through bedrock. So the model is capable of doing that. We have only one snow layer, not multiple snow layers, one layer of vegetation, and you can see all the processes here. So this is the state of the model as it's implemented in Kinesim 5. Okay, so in terms of configuration, and we are not calling this model classic yet, and I will tell you the reason why. So as it's implemented at that time, the model was called class for the physics component, and Canadian Terrestrial Ecosystem Model CTEM for the biogeochemistry. So it has 3 soil layers. So despite the ability to do all these soil layers, unfortunately, that version of the model has only 3 soil layers. The top layer is only 10 centimeters. The layer below it is 25 centimeters. And then you have, boom, a huge soil column of 3.75 meters. So the maximum soil depth the model does is 4.1 meters. And this maximum depth is comparable to other models. If you look at CLM, they go down to 7 meters. The cable land surface scheme in Australia, they go down to about 5 meters. The physics is done for 4 vegetation types, needle-leaf trees, broadleaf trees, crops, and grasses. And then when we included the carbon cycle, all we did was we took these needle-leaf trees and we split them into evergreen and deciduous. We did the same thing for broadleaf trees, evergreen, but we also split into cold and drought deciduous trees. And you need to do this if you want to do the photosynthesis and the carbon cycle properly. And crops were divided into C3 and C4, and grasses into C3 and C4. And C3 and C4 are 2 photosynthetic pathways through which vegetation photosynthesizes. So trees are usually C3, but crops and grasses can be C4. And in terms of primary prognostic state variables, sorry, this should be prognostic. On the physics side, you have the liquid and frozen soil moisture contents of the soil layers. You have soil temperature, and like I said, a single snow layer whose thickness is a prognostic variable, as well as the fractional coverage of snow is a prognostic variable. On the carbon cycle side of the things, the primary prognostic variables are vegetation carbon and soil carbon. And so what happens is vegetation can grow and die in a grid cell depending on the climate. And when vegetation grows and dies, so if it doesn't rain, for example, someplace, then over time, vegetation will just shrivel away. And as the vegetation is changing, it changes leaf area index, rooting depth, vegetation height, which affects the roughness length, and all these other vegetation attributes. So vegetation becomes a dynamic component of the model with C10. Okay, so I mean, this is obvious, but because there are a lot of students here, I think this is worth mentioning. So up until CMIP 5, we were a physical climate model. For CMIP 6, we included land and ocean carbon cycle model, and Jim and Neil are going to talk about the ocean carbon cycle today. And what this means is you can then simulate the flux of carbon between atmosphere and land and atmosphere and ocean. And this arrow, the flux of carbon between land and ocean, this arrow took me 5 years to do this arrow. So that was the development of the land carbon cycle model. And the idea here is if you are simulating the flux of carbon between land and ocean dynamically, you can, of course, do emission-driven simulation. So you put emissions in the atmosphere, land and ocean will do their thing. They will react to change in CO2 concentration in the atmosphere, and you can simulate the evolution of carbon burden in the atmosphere or your CO2 concentration. So that's your typical emissions-driven simulation. Alternatively, you can also specify CO2 concentration, and that's what we call concentration-driven simulations. And again, land and ocean will do their thing. They will respond to increase in CO2 concentration in the atmosphere and the change in climate, and you can back out these emissions. And you can then say, if you want to achieve this CO2 pathway, this is what the model says the emissions should be. So CANI-SIM 5 can be driven in both these emissions and concentration-driven modes. Okay, so on the physics side, this is the global hydrological cycle, and we are not trying to use this routinely because, again, the spatial structure of the fluxes at the land surface will evolve in response to what the climate is doing. But we always try to make sure that the globally average numbers are reasonable, so be it globally average temperature or something else. So in this case, for global hydrological cycle, you can see that the precipitation over land, the ones in black and gray, these are the two observation-based estimates. And the ones in light orange and dark orange are numbers from pre-industrial run and historical run. And you can see we're a little bit higher on the precipitation side for CANI-SIM 5, but we are well within observation-based estimate. So that gives an idea, and runoff is around 45 units. And of course, over the long term, vapor transport from ocean to atmosphere must be matched by freshwater flux from land to the ocean because hydrological cycle is, of course, closed. Okay, so that gives you an idea that the model overall is pretty reasonable in terms of global hydrological cycle. Okay, so amongst all the other carbon cycle processes, the model also includes the ability to include land use change. Now, land cover is prescribed for the historical period and future scenarios. So land cover is read from a file. So once you go through the model, and there's a file called canism.config file, if you look at that, you will see along with other greenhouse gases and emissions, there's a file that has land cover in it, and it has the prescribed fractional coverages of the 9 vegetation types that C10 considers. And what this means is, although the vegetation grows up and down in a grid cell depending on the climate, it doesn't change spatially. So if the climate warms, in this version of the model, the vegetation is not going to move polewards, for example, in the northern hemisphere. So with that limitation in mind, you can still see how land use change affects climate. So on the right-hand side, there's a plot, and you can see this is the change in crop area. So over the historical period, crop area increases by about 10 million square kilometers, and that increase has to come from somewhere. So in this case, of course, it comes from trees and grasses, more or less in equal proportion. And then going in the future for different scenarios, you can see the crop area is increasing in most scenarios, and the areas of trees and grasses is decreasing. So all these files are there, and what this means is you can also change the land cover. So and Kirsten is trying something like this with Kennythem 5. She wants to see the effect of afforestation or reforestation. So all you have to do is change the land cover file, put together the land cover file, the model will read the land cover file, and you can simulate the effect of afforestation or deforestation. So, and you can do that both in emissions and concentration-driven simulations. And of course, if you grow trees through afforestation in an emissions-driven simulation, then land will suck up carbon, and that will affect the CO2 concentration. So the model has the ability to do this. Okay, however, the model has its limitations. Those three soil layers that we have, specifically the third soil layer, which has a huge depth of 3.75 meters, what happens is as you run the model forward, that it has a huge inertia. It's a 4 meters soil block that has to be thawed. And what happens is it doesn't thaw, and boom, then the whole thing thaws. So to do permafrost properly, you have to have more soil layers, especially near the surface. And you need to go deep because you have that thermal inertia from the pre-industrial run. So none of those things are present in Kennythem 5 in Class CTEM, and as a result, the permafrost extent is simulated pretty badly. So you can see here, compared to observations, which say permafrost extent is 15 million square kilometers, the number we get is around only 3.2. And these are all the other models from CMIP 6. The other limitation the model has is, despite the fact that it simulates carbon uptake over the historical period reasonably well, and as a result, we get the right CO2 concentration and or the right diagnosed anthropogenic emissions over the historical period, its carbon uptake, especially for high emission scenarios or high concentration scenarios, is really high. So these are all the CMIP 6 models, and you can see Kennythem 5 had the highest land carbon uptake. So this is this number here, 1204, compared to these other models. And then the models in red are the models which include nitrogen cycle. And we know when you include the nitrogen constraint, then the model doesn't go crazy when it sees increasing CO2 because photosynthesis is limited by nutrients. Now, in most cases, this doesn't matter, but if you're diagnosing emissions or if you are simulating CO2 prognostically for a given emissions pathway, then of course this matters. So I'll leave it there for that we were one of the models with the highest land carbon uptake. So with these two limitations in mind, CMIP 6 was a long time ago. And now we are already moving towards CMIP 7. And over the years, so Diana Versaghi, who wrote the physics component of the land surface model, she retired. And then both the physics and the biogeochemistry were combined into a single model, and the model is now more coherent. And we renamed it to CLASSIC, Canadian Land Surface Scheme, including biogeochemical cycles. And Joe Melton in our group, he launched CLASSIC as a community model in 2020. And so not only we have Classic or Class CTEM contributing to CMIP-related activities, we can also run the model offline in a standalone mode on a single site over a given region or even over the whole globe. And we routinely run it over the whole globe offline, and it contributes to land-focused MIPs, such as, for example, Trendy, which contributes to the Global Carbon Project. And both coupled and standalone activities are essential to model development. Okay, so I do not know how much time I have left, but I'll try to go a little fast. So for CANeSIM 6, and this is also in CANeSIM 5.2, we have improved our soil profile. So we have 15 soil layers in the top 4 meter, and below that we have 58 meters of bedrock. So it's already allowing us to do permafrost properly. So like I said, there are 2 things to do permafrost properly: more soil layers, and you go deeper. And we are also working to include nitrogen cycles. So here's that same figure again, but now you can see you have this nitrogen cycle as well. So the model fixes nitrogen through biological nitrogen fixation. There is nitrogen deposition, and then you also simulate, it has, of course, nitrogen cycle has to be completed. So you have ammonia volatilization, and you have emissions of all these nitrogen-related species, NOx emissions, N2O, and N2 emissions. So the model is, for CMIP 7, the model is able to do this. And we're still working to clean this up. But for CANeSIM 5.2, which I think, as I understand, the community will, the CP4C community will have access to, you will have that higher soil discretization, more number of layers, but you will also have fire in the model, and fire will allow, and here's a comparison of the red lines, and the red and the orange line are model simulations, and the black line is observations. And you can see most of the area burned is in the tropics, the north and south of the equator, as ITCZ moves up and down, and the model is able to reproduce that. What we are not able to get is these high latitude fires in Canada and Russia. Those are much harder to do, and we are working to improve those. But globally speaking, 88% of the emissions and area burned happens in the tropics, and we're able to do that. Okay, and in terms of spatial distribution of area burned, right-hand side, this is area burned in Classic offline. And again, like I said, you burn a lot of area north and south of the equator. The model captures that. We burn a little bit more in the Amazon because, as everybody knows, it rains a little bit less in the Amazon in the model, and a little bit more in South America. But overall, we don't burn down the whole world. Or Amazon for that matter. So the area burned is reasonable. Okay, so to summarize, Class CTEM is the component available in CANeSIM 5, which is what we use for CMIP 6. The model grows vegetation dynamically, but the fractions are prescribed, so the vegetation cannot respond spatially to change in climate. Model limitation includes its 3 soil layers and excessive carbon uptake. And we have addressed these limitations as we have transitioned to Classic, and the more number of layers and fire will be available in CANeSIM 5.2. Nitrogen cycle will likely not be, because we are still trying to make it work within CANeSIM 5.2 framework, and eventually this will go into CANeSIM 6 as well. All right, so I will stop here. Thank you.
Thank you so much for that. That was so informative. Kirsten, you have a question?
Yeah, I do. Thanks, Vivek, for this great overview. So a couple of very quick questions. So you mentioned the high land uptake and the CMIP 5 version of the land surface model. So I remember previously you used downregulation of photosynthesis to address that and also kind of mimic nitrogen limitation. So did you do that in CMIP 5 as well?
Yes, we did. We do have down regulation. So what happens is, and I have a better understanding of this now, is that over the historical period, not only CO2 emissions are increasing, but nitrogen deposition has also increased. So if you only have carbon cycle in the model, you have to tune your model not only to have it respond to increasing CO2, but also increasing deposition. So to get the right CO2 uptake over the historical period, you come up with some parameter. Going into the future, most scenarios, nitrogen deposition reduces because of the clean air regulations, but the CO2 keeps on increasing. So the model parameter, which was tuned over the historical period, which takes into account both CO2 and nitrogen deposition, actually doesn't work going into the future. And that's why in our model, you end up with a higher carbon uptake. So those results I showed from CMIP6 models, they were for 1% CO2 simulation. And of course, 1% CO2 simulation, CO2 quadruples, as you know. So that high CO2, somehow the model believes that nitrogen deposition is ongoing, but it's not. So that's, I think, the reason the model ends up sucking up carbon too much. We're trying to see if we can relate that down regulation somehow to nitrogen deposition as well. And that would be one way to do it if nitrogen cycle isn't working. But we are working very hard to make sure we have nitrogen cycle in the model. We have it offline, but this is the very first time we'll have to make it work in the coupled model. And as always, nothing is straightforward.
Okay, thanks. And very quick question. So what are the plans to implement dynamic vegetation in Classic?
So dynamic vegetation, it's again, we have it working offline. It's in the code, but whether we will be able to get it working for CMIP 7, I do not know. Again, it's a time and effort and human resources issue. So nitrogen cycle is higher on my list to get it working, because remember, last time half of the models had nitrogen cycle over land. This time, I believe all of them will have it. So if we don't get it in, we'll look pretty bad. Dynamic vegetation, only 2 models last time, MPI and UK Earth System model had dynamic vegetation. So that's why I put dynamic vegetation on my list further down. But if we get lucky and nitrogen cycle just works straight out of the box, which I think it won't, then we will include dynamic vegetation. Otherwise, at least the idea is to get fire and nitrogen cycle in.
Okay, thanks a lot.
Thanks.
If you have questions.
Yep, go ahead. Zihong Zhu.
Jiyoung, we don't hear you yet. I don't know if you had to reboot your computer, I saw, so I don't know if it's working right. Maybe I'll just ask a quick question. Yeah, Jiyoung. Just wanted to ask a quick question, Vivek. Taking up on the fact that Classic is a community model that's been running separately for several years. How useful has that been for your model development process? Like you have, it sounds like there's a lot of detailed work that still has to happen in-house, and the challenges remain. But has there been some have you been able to use that larger community to leverage some of the work and make it go more efficiently? I guess it's a question for Joe, who isn't here, but just to ask you what you've found yourself.
Yeah, so that's a difficult question to answer, Paul. So like Neil said, everything. So there are 2 aspects of community involvement: application of the model, and 2 is bringing new science in and incorporating that into the model. So application-wise, yes, we've definitely seen a lot of application. In terms of bringing new science in, there are a couple of projects that are already happening, but the science from those hasn't been brought in yet. And again, the idea now is not that Classic is implemented in CANeSIM 5. The idea is you test your model offline, make sure everything works, but then you also bring it in the coupled framework, because as I've learned, coupled modeling is not intuitive. Offline is pretty straightforward. If you simulate a little bit higher evapotranspiration or lower evapotranspiration, 2 to 3%, you will be within observation-based estimates, and you're running the model offline driven with precipitation read from a file. If you mess up your evapotranspiration in a coupled model, it will have feedbacks. If you have low evapotranspiration, it will rain low and the model goes into a drier state. So a coupled model is a more stringent test of what you're doing to your model. So anything that goes in classic will have to be tested offline and then the coupled model as well. And we were not able to do this for a very long time because classic had not been implemented in Kinesis framework, but now it has. And we are already seeing so many surprises that things that we thought were okay offline, well, they were not okay when we coupled the model. So that's why I'm saying both offline and coupled modeling go hand in hand. Offline, you drive the model with observations. Coupled, there are feedbacks. The difficulty is coupled, the model is not perfect. There are climate biases. So both those things are essential to do land development. So sorry, my answer is not complete, but I think the answer is science-wise, it hasn't helped as much as we thought because of all these additional complexities.
Yeah, it definitely is food for thought, and it's not surprising, but I think it's good to manage expectations, right?
Yeah.
And you're getting a community of lots, maybe more and more experience of applications, and that's good. But when it comes to actually, as you said, adding science to the model, doing new development, it's very testing. And we can talk about that later. We don't have to figure it out now, but
Yeah.
I make sure while I had you here to.
Yeah, thanks.